Now have a theorem. A Hilbert space has a countable orthonormal basis, that means a complete orthonormal set, if and only if it is separable. So proof. So existence of a countable orthonormal basis is equivalent to saying the space is separable. So this is why separable Hilbert spaces are very important, and almost every Hilbert space which we come across in applications is separable. Okay, so we will prove this way. So it has a countable orthonormal basis. So En n equals 1 to infinity is an orthonormal basis. Therefore, we just proved that the span of the n in n is dense in the Hilbert space. Now that means every so x is in H, then x can be approximated as closely as we wish by a finite linear combination with of the En. So, and hence by finite rational linear combinations. That means every x can be approximated as closely as possible by sigma alpha ei. If we are in a real Hilbert space, we can take alpha i's to be rational. If it's a complex Hilbert space, we can take the real and imaginary parts of the alpha I to be rational, and therefore, and these rational combinations of the En form a countable set. So rational linear combinations of En is countable and is dense in H, and therefore H is separable. Conversely, let us assume that H is separable. So we have Xn n equals 1 to infinity is a countable dense set. So now let Ei I in I be an orthonormal basis, and let us assume I infinite, because if it's finite we have nothing to say. So, and therefore if I is an infinite set, and now we have that Ei minus Ej norm square is always equal to 2 if I is not equal to j, and therefore if you take the ball, center Ei and radius say root 2 by 4 to be absolutely safe, then for all I in I, these are all disjoint, all mutually disjoint. But then these are all open balls, so each ball must contain at least one Xn, and each Xn can belong to at most one such ball, because the balls are all disjoint. You can't have a common element in two of them. So since xn's are countable, so this means, so every ball must contain, and there are only countable number of these, and therefore I is countable. Okay, so countably infinite, and therefore H has a countable orthonormal basis. Okay, so that is the okay, so now for time for some examples. So if you have ln2, then you take EI to be the standard basis. This means 1 in the ith place, 0 elsewhere. So this is an orthonormal basis for ln2. Because the EIs are all of norm 1, the EI, EJ are orthogonal to each other, and any x can be written uniquely in terms of the EI, and therefore this forms a basis, and it's therefore a maximal linearly independent set, therefore it's maximal orthonormal set as well. So L2, so again En, n equals 1 to infinity, this is an orthonormal basis, because every if you have sigma, if x equals x1, xn, etc., then x super n equals sigma I equals 1 to n xiei, and this is what, x1, xn, and then 0 after that, and this xn converges to x in L2, and therefore all linear combinations are dense, and by an earlier corollary we have that En is a complete orthonormal set, and therefore it's an orthonormal basis. Okay, so now another example. So this is the Fourier series. Okay, so let us consider L2 of minus pi pi. So you consider the set F0 union Fn Gn n in n. Okay, so what is F0 of t? Is 1 over root 2 pi. Is identically equal to this. Fn of t equals cos n t by root pi, and Gn of t equals sin n t by root pi. Okay, so t belongs to minus pi pi. So this is an orthonormal set. That is clear to see. You can very easily check that all these things have norm 1 and that they are all orthogonal to each other. Okay, so this is an orthonormal set. Okay. Now, continuous functions with compact support in minus pi pi are dense in L2 minus pi pi. Okay, and because they are of compact support, you have that such functions. So phi belongs to Cc of minus pi pi, then phi of minus pi equals phi of pi equal to 0. So phi is automatically 2 pi periodic. So if you consider the span, so let me call this set E, then is dense in continuous 2 pi periodic functions on minus pi pi, and in the uniform topology, that is in norm infinity, that is a sup norm. Okay, that means every continuous 2 pi periodic function can be uniformly approximated by means of a function in the span of E. This is nothing but the Stone-Weierstrass theorem. This is a theorem in analysis. And since we have minus pi pi has finite measure, so this implies that span of E is also dense in CC minus pi pi, and hence in L2 minus pi pi in the 2 norm. Because if it's in the L infinity norm, sets of finite measure, L infinity is continuously embedded in L2, and therefore it is true in this. Therefore, the span is dense, so this implies E is an orthonormal basis for L2 minus pi pi. So we have proved the completeness. So this is an example of an orthonormal basis in L2 this. So that means, what do you have? If f belongs to L2 of minus pi pi, you can write f of t equals, so integral minus pi pi of ft into f naught, which is 1 by root 2 pi dt, into 1 by root 2 pi, okay, plus sigma n equals 1 to infinity integral minus pi to pi of ft cos nt dt by root pi into cos nt by root pi plus sigma n equals 1 to infinity integral minus pi to pi ft sin nt by root pi dt into sin nt by root pi. Okay, so we can rewrite this as ft equals a naught by 2 plus sigma n equals 1 to infinity an cos nt plus bn sin nt, where a naught is 1 by pi integral minus pi to pi ft dt, and an is 1 by pi integral minus pi to pi ft cos nt dt, and bn equals 1 by pi integral minus pi to pi ft sin nt dt. So this is the classical Fourier series. We have already seen this on an earlier occasion in the connection with the uniform boundedness principle. Okay. So we call an a naught and an bn n equals 1 to infinity as the Fourier coefficients. Okay. And what does it mean? If you have fn of t equals a naught by 2 plus sigma n equals 1 to capital N an cos nt plus Bn sine nt, then Fn will converge to f in L2 minus pi pi, that is limit capital N tending to infinity integral minus pi to pi of mod Fn minus f whole square dt is equal to 0. So in this sense it converges. So if we have seen the uniform bounded principle that pointwise convergence is even for continuous functions is not guaranteed, whereas in the L2 norm the Fourier series always converges to the corresponding L2 function of minus pi pi. Okay, and if you take Parseval's identity, what is that? Integral mod f square minus pi pi is okay, so that is given by the sum of the squares of the inner product with the Fourier coefficient. So that is Parseval's identity, and if you rewrite that, you will get 1 by pi mod ft square minus pi pi is equal to a naught square by 2 plus sigma n equals 1 to infinity of mod an square plus mod bn square. Okay, so this is how what it will work out to for the Fourier series. Okay, so you have in fact a and bn should all go to 0 because of this condition. Okay, so now another example. This is the Fourier sine series. So let us take now L2 of 0 pi. So this is our Hilbert space, and then you look at the set E to be root of 2 pi, root of 2 over pi sine nt n in it, n equals 1, 2, 3, etc. So again, this it's easy to check. This is an orthonormal set in L2 0 pi. So each one has norm 1 and they are all orthogonal to each other. Okay, so now let us assume we want to show that this is in fact complete. So let f belong to L2 0 pi such that integral ft sine nt minus pi to pi dt equal to 0 for all n in n. So that means the inner product with these functions in E are all 0. We will then show that f is identically 0, and therefore by one of the characterizations we will show, we know that this is a complete orthonormal set. Okay, so now what you do is you extend f as an odd function to minus pi pi. So you take f of minus t equals minus of f of t for t positive. Okay, so f of minus t will be negative. So in the negative range, you define it as minus of f of t. Okay, so then this is an odd function. So now, and of course, this new function f will now belong to L2 of minus pi pi. Okay, now what about ft cos nt integral minus pi to pi? Now this dt, now this is an odd function, cos is an even function, so the product is an odd function. An odd function on a symmetric interval will have integral 0, and so this will all be 0. And then integral minus pi to pi ft dt, the constant function. So this just again f is an odd function, so this is also 0. Now what about integral minus pi to pi ft sine nt? Now because both of them are odd, sine is odd, ft is also odd, so the product is an even function. This is twice integral 0 to pi of ft sine nt dt, and that is given to be 0, given. So f with all the cos nt, sin nt and the constant function, the inner product is 0. So since we know that these functions form a complete orthonormal set for minus pi pi, so this implies that f equal to 0 on minus pi pi, therefore f equal to 0 on 0 pi also, and therefore E is an complete or orthonormal basis for L2 of 0 pi. Okay, that means any f in L2 of 0 pi, then you can write ft as sigma n equals 1 to infinity bn sin nt. Okay, and this will converge in the sense of L2, and this is called the Fourier sine series of any function in the space. Okay. So now we, by analogy, so H is separable Hilbert space, and En n equals 1 to infinity is an orthonormal basis or complete orthonormal set. Then we know any x in H, then x can be written as sigma n equals 1 to infinity x En En. So this is called the Fourier series for x, and you call x En are the Fourier coefficients. Okay, now since we can write this like this, so x is in fact the limit of n equals 1 to n, n tending to infinity, sigma n equals 1 to capital N, x En En. So the set En is called a Schauder basis. So we have two kinds of bases. We have the Hamel basis. So this is a algebraic basis. That means every x in H is a finite linear combination of basis elements. So this is the basis as we know it. A Schauder basis is a sequence x1, x2, xn. So Schauder basis, so we have x1, xn and so on, a countable set, and given any x, then x can be written as limit n tending to infinity sigma I equals 1 to n alpha I xi. If you can write it like this, then we say it's a Schauder basis. So this definition holds in any Banach space, and so every separable Hilbert space, so every separable Hilbert space has a Schauder basis, namely the orthonormal basis. Now if you look at little lp, so again if you look at the sequences En, these are the sequences with 1 in the nth place and 0 in all other terms. So this forms n equals 1 to infinity, forms a Schauder basis for LP 1 less than or equal to P strictly less than infinity. It's not true in L infinity. It also forms a Schauder basis in C0 for instance, and so on. We have used these properties before. Okay.